When we were finding derivatives of those power functions, we had to expand out some power of a binomial like what we have here. And to do that, we used a device called Pascal's triangle, which of course we remember from algebra or from pre-cal. And the way you make this thing, so we start with ones along the outside here, and then all the numbers that are on the inside come from the sum of the two numbers right up above it. So like 35 comes from 15 plus 20. This 120 comes from 84 plus 36, and so on. And we use these numbers to form the coefficients of each one of our terms of our expanded binomial. So this 1, 4, 6, 4, 1, of course, are all the coefficients here. I can see a 1 understood there, 4, a 6, a 4, and another understood 1. So let's use Pascal's triangle here to expand out x plus c to the third. And yes, I understand that you know how to do this, but I'm going to try to make some kind of generalizations and some connections that are going to help us with our proof of the power rule for taking derivatives. Okay, so whenever I go to expand this out, I need to use the third level. It's actually not the third level, right? It's because it's right here. This is actually the fourth one down. But it's the third level if we say this one is x n equals 0. So it's like this. It's x plus c raised to the 0 power, which of course should be equal to 1. So this is our third level. This is the one that we want to use, 1331. We know this one. That's one that most people remember. And those are supposed to be our coefficients. So when we start this, it's 1 times x, but I never write the 1 down, so I'm just going to write x raised to the third power. And that third power is the same power that we're raising this whole thing to. And now all of the exponents for x are going to start counting down, and then I'm going to start introducing the c's, and their exponents, of course, are going to count up. Plus 3 x to the second, it just counted down 1, and now I'm going to start introducing my c's to the first power, plus the next 3 x to the first power, c squared. It's going to start counting up, of course, and then finally plus 1 c to the third power. All right, let's make a few connections here. First of all, each one of these terms is cubic. That one's cubic, obviously. This whole thing is supposed to be cubic. This one's cubic in disguise because this would be to the first power, and we multiply these. We add these exponents 2 plus this understood 1 is 3. Same thing here, and that one's 3. So all the exponents are either 3 or they're going to add up to 3 for this case. Speaking of 3's, don't we have some 3's in here? We sure do. Here's a 3, and there's a 3. Those two 3's are exactly the same. That is your n value. Your n is equal to 3 in that case. But also, so is this one. That 3 is also from that n power. That's right there. Boom. Now, let's look at the exponent of 2. So this exponent of 2, that's 1 less than this power, right? One way to write that would be that was n minus 1. It's 1 less than that. The exponent on the x that's right here for this linear, this one that's 3x, it would be a 1, which would be, let's say, n minus 2. Okay, so I bring this up because what we're going to try to do is generalize raising some sort of binomial to any particular power. And the reason why is because whenever I go to prove the derivative y equals x to the n, I'm going to have to raise x plus h to the nth power within the limit definition. So in some kind of way, I have to wrap my head around when I don't have a number up here and I have something that's variable that can change and increase to as big as I want it. How do I expand this thing out? That's what our goal is, to try to understand. And making these kind of connections are going to bring us there. All right, now, when you make Pascal's triangle, don't you need one of the levels in order to get the next one? In other words, in order to get this 56, I need to know the 21 and 35. And in order to get the 21 and 35, I need these numbers that are up above it, which means that I need the numbers up above it, and so on. But is there a way to get, let's say, this 121 without all of the stuff that's up above it? And the answer to that question involves something called the binomial theorem. Okay, so in the expansion of x plus c to the nth power, this is what it looks like. So notice that this power here, let me get my laser pointer here, this power n is the power on that x right there, all right? And for the very next term here, this n is the same exact variable, whatever that number is. If it's a 3, then that's a 3. If it's a 4, it's a 4, and so on. And then the next power you decrease by 1, and you continue to decrease the powers. But what about all of the other coefficients? Instead of having to use the Pascal's triangle and get every single number up above the one that you actually need, we're going to use something called a combination. So that is what the formula is right here in blue. This is n factorial over n minus r factorial times r factorial. And the little exclamation point that means factorial, it's not super excited. It means, for example, if I have 5 factorial, it means 5 times 4 times 3 times 2 times 1. You take the product of all the numbers that come before them down to 1. And this is something called a combination. So in order to understand combinations and to understand this formula before we dissect it a little bit, what I would like for you to do here, I'll come back over here since that crashed on me, and I'm going to ask you a particular question. I want you to think of a group of 5 people. You have 5 people. And my question is, how many ways are there to pair up those 5 people? So, for example, you can just think of a table of 5 people, and you want to just take a pair of those. How many different ways can you pair up those people? So we're going to stop the video here, and I want you to see if you can figure out how many pairs of people in some kind of way. Maybe you assemble in your family 5 people, and then you count them out in pairs. Or maybe you make some sort of diagram. I don't care. You see if you can figure it out.